Hi guys, welcome back. In the last video we have seen the loss function. We derived our loss function and this was the objective function basically, okay, and we wanted to minimize this objective function with respect to a1 and b. Okay, so let's proceed further with the optimization part. Now in optimization, what we are going to use, we are going to use gradient descent. There are various variant of gradient descents available in your multivariate calculus. So one is SGD, that is stochastic gradient descent. Another is adaptive gradient descent. Okay, so ADAGRAD, it is known as ADAGRAD. Another is RMS prop. So a lot of variants are available of this gradient descent, but we will be using simple gradient descent, and we'll talk about all these variants in our later videos when we'll talk about the optimization or neural network. But here we'll just use the basic gradient descent that is basically used in many of the machine learning algorithms. Okay, so let's see what was our loss function. This was our loss function basically. So loss function was given by loss is equals to 1 by 2, and we saw how we why we are using this 1 by 2 and why we are multiplying it with the actual total cost, and why we are squaring this total cost. We have already seen that. If you are not familiar with the reason why we are doing this, you can just go and watch my previous video, right? So yi cap minus yi whole square. This was our loss function. Okay, so we'll be applying gradient descent, and in the gradient descent what happens, we basically, since this function is we want to optimize this function with respect to a1 and b. Okay, this is weight, and in mathematics we say it as slope, and this is bias. Okay, and we say in mathematics this is intercept, right? We are talking about simple gradient descent. Now we want to minimize this loss function with respect to a1 and b. So what we'll do, we'll try to move let's say that our loss function is something like this, convex in shape, and this is the minimum point. Okay, minima, global minima. So what we want to do, we will start from a point. Let's say that we have this a1 here, okay, and let's say for a given b, this is our loss function. Okay, so what we'll do, we'll basically try to move our try to find out the values of b and a1 so that the loss is minimum. At this point we want to find this b and a1. Okay, a1 dash and b dash. Okay, we want to find out this. So what we'll do basically, first we'll try to differentiate this function. First we'll differentiate this function with respect to a1. Okay, so what is the meaning of this differentiation? This is basically nothing, but it gives us a direction in which the loss function is decreasing fast with respect to a1. You are understanding it? Let me explain it. This dou loss by dou a means that when I change a1 by a very small quantity, what is the change that is going to happen in loss? Okay, what is the change that is going to happen in loss with respect to a? So that is why I'm saying that this dou loss divided by dou a1 gives us the direction in which the loss function decreases faster with respect to a1. Okay, so the steepest direction towards which loss function goes with respect to a1 when we change a1 is given by this term dou loss by dou a. Okay, don't worry, we'll talk about this term more when we'll talk about the gradient descent and its variants. Just remember that when we apply gradient descent, you need to find out the derivatives with respect to the weights, okay, and derivative with respect to the bias. Okay, so here only one weight is present and we already have the loss function, so we need to calculate the derivative of this loss function with respect to a1. Okay, so when we'll calculate it, you will just see that the usual mathematics, if you are not familiar with the calculus, then you can skip it basically, but you need to remember this term here, that we are getting this term here. Okay, so after calculating the derivative, so dou loss by dou a1 will give us this term. So what is this term? This is nothing but the summation of the product of the independent variable with the cost with respect to that variable. Okay, so we take the summation of all, and that will give this derivative term with respect to a1. And similarly, we are going to find out the derivative of loss function with respect to bias term, right? So in multilinear regression, we'll be observing that we need to calculate dou loss by dou a, dou a1, dou loss by dou a2, dou loss by dou a3. So a lot of weights will be there, and after calculating all derivatives with respect to all the weights, we'll be calculating this derivative with respect to the bias term. Okay, so when we'll calculate the derivative with respect to the bias term, this will be nothing but this term here. Okay, that is this term. Okay, so you need to remember these terms because they will be used when we'll update the weights. Okay, after calculating them, the next step is to calculate the new weights. So basically we need to update the weights. Okay, we need to update the weights. So the formula for updating the weights will be old weight, that is whatever we considered in the initial stage. We considered, let's suppose that initially I said that my weight and bias terms are all 0. Then what will happen, that new weights will be old weight minus this L is, in calculus it is known as step, but in machine learning this is known as learning rate. Okay, learning rate, and it is basically kept 0.001 in most of the cases. Why do we keep our learning rate very less? Let's see in this term, in this graph. Okay, so let's suppose that this is our global minima. Okay, and here we are. Let's suppose that the values that we are getting, okay, for let's say a1, initial a1 at iteration, let's say t, we are here. And if we'll take learning rate much higher, and let's say that the direction or the derivative with respect to derivative of the loss function with respect to a1 we found out, and it is pointing towards this direction. Okay, so what will happen when we'll take L as a very large number, let's say something capital K, a very large number, then it will take, basically it will move to this direction with that K step, that learning rate K, and in single iteration it will jump to this position. Okay, it will jump to this position. Then what will happen in the next iteration, it will again find the direction, and let's say that direction is this, and learning rate we have taken very large number, so it will again jump to this position. And again let's say the direction is in this direction. Okay, and learning rate is really high, then it will move to this direction. So you can see that the convergence will take a lot of time, because the point or the newly generated points will oscillate from here to here and here to here and here to here. Then after many iteration it will get converged to the global minima, right? And if we take K very small, let's say that we have taken K as 0.001, then what will happen, let's suppose that L is this small number, then what will happen, we'll find this direction, and in the next iteration our loss will be decreased to this point. Okay, so we'll move to this point here. then again in the next iteration we'll move to this point, again in the next iteration we'll move to this point. So on an average we'll be moving like this, we'll be following the same graph very slowly. Okay, so there will be no oscillation, like we'll not be jumping from left side to right side of the global minima and from right side to left side of the global minima with each and every iteration. Okay, so basically you should remember, whenever it is asked that why do we keep learning rate smaller, then you can say that smaller learning rate basically helps gradient descent to converge faster. It helps in avoiding oscillation. Okay, so that is the thing that you should remember for the interview. So you'll be updating this, updating your weights. So this will be your new A1 and this will be your new bias. So old bias, and you will be subtracting this factor here, derivative with respect to b, and you will be multiplying this with this step or learning rate, and you will be subtracting it. Why this minus sign is here, they can ask. It's a very basic question basically. So let's suppose that you are here, let's suppose that let's suppose that this is loss, okay, and this is my A1, okay, and we are at this position right now. Let's say this is A11 at this position. So what will happen when we'll calculate the slope at this point? It will be something tan theta and some positive number will be there. Okay, some positive number will be there. So, and when theta is positive, it means that our global minima is on the left side of the current point. When the slope is positive, it means that the global minima is on the left side of the current point. Okay, so if you want to move back, so basically it is obvious, if we want to reach to this global minima, then we need to decrease our A1, right? That is why this negative sign is there. Okay, and when we'll be at this side, on the left side of the global minima, and we'll find the slope, it will be nothing but some tan theta that will be negative. Okay, and since it is giving us negative value, it means that the global minima is on the right side. So if you want to take the right side, then we will have to add something to the current A1 or current weight, right? That is why when this derivative term, that is the slope, will be negative, the negative will become plus and it will get added, right? And when this is positive, it means that we need to decrease the weight, current weight. That is why it is negative and we need to subtract from the old weight, right? I hope you got a little bit idea from that. And after you got these new weights, you need to just calculate again calculate the new weights in the next iteration by placing these new weights in the position of old weights, placing this new bias in the position of old bias, and you need to calculate new bias in the next iteration. So this whole process repeats again and again until you reach your global minima. Okay, so you take the steps like this, and you slowly reach to your global minima, right? And after you get to the global minima, what happens that the difference between the loss change, the change in the loss becomes very, very small, and your loss becomes very, 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 very less. That is 0.00 something. Okay, if you'll take too much of iteration, it will become almost zero, right? So this is basically the mathematics part of this linear algebra, and linear regression, and we'll be now we'll be seeing the code that will implement this linear regression, and we'll be looking after the codes. We'll be looking at some projects, some real-time projects, like the projects that will be utilizing the data that is available over the internet. We'll be using those data sets, and we'll be trying to predict, we're trying to check whether we are getting best fit for that data or not. Okay, and after that we'll talk about some interview questions related to linear regression. Okay, so in the next video I'll be making a program or algorithm for linear regression from scratch, but I'll be making a program for multilinear regression basically. So I'll basically tell you the difference in the program itself, so it will be easy for you to understand, because it is not needed to repeat all this process for multilinear regression itself, because the process is very similar basically. Okay, in place of this x single independent variable, we'll be having multiple independent variable in multilinear regression problem. Okay, so thank you for watching. Subscribe to this channel if you are getting a little bit benefit out of this. Share this video, like this video, and let me know if you want some improvements or if you want something new from this playlist. Okay, thank you for watching. Bye.